In this lecture, we're going to be talking about social interactions and how individuals living in social groups can influence each other's ecologies and evolutionary histories. Let's first talk about a common misconception that people have about social living. Social living species are not necessarily more advanced or more evolved than solitary species. Both living arrangements, living solitarily or living in big groups, have various costs and benefits in different ecological circumstances. So, for example, when it comes to being seen by predators, being in a group has a negative aspect in that you're more conspicuous when you're in a clumped group of individuals to predators. But as we talked about previously, defense against predators via the dilution effect or mutual defense or a better detection of predators as they approach can sometimes counteract this cost and actually be a net benefit. Living in groups sometimes can lead to greater transmission of disease and parasites among group members. But one benefit of living in a group is that you may receive assistance from others in dealing with pathogens like ticks. Mutual preening is one of these benefits. There could be increased competition for food in groups, but again, being in groups may allow you to be able to find food more efficiently. We talked about the information center effect. Time and energy expended by subordinates in dealing with more dominant competitors in a social group may be a problem for the subordinates, but again, the subordinates at least are given permission to remain in these safer groups. They may be making the best out of a bad job. They may not have as high a mating success as dominant individuals or get as much food as the dominant individuals, but they still might be better off living in the group than they would be on their own. There's the potential for greater male vulnerability to cuckoldry in groups. One individual's loss is another individual's gain, so one of the benefits of being a group is having the potential to cuckold other males. Females also have problems associated with reproduction in big groups because of intraspecific brood parasitism, egg dumping, egg tossing. But again, some individuals will be losing out in these interactions and other individuals could be benefiting. So to give you a few examples, acorn woodpeckers live in many cases in just monogamous groups where there's just a male and a female. But in other cases, there are multiple males and females that live together into these, what we discussed previously as polygynandrous mating systems, in which all of the females will share a single nest and they'll all lay their eggs into this single nest. Now, one of the benefits of this is they share incubation duties, and one of the main sources of mortality for females is being attacked in the nest while they're incubating. And so this kind of distributes that threat among multiple individuals. However, a cost of this is that females will compete to make sure that they have the most eggs in the nest, and they'll toss each other's eggs out until they begin to lay themselves. So the subordinate individuals will begin laying eggs. Dominant individuals would come in, and before they lay their own eggs, they'll chunk out some, but not all of the subordinate individuals' eggs. Just enough to keep them interested in helping with the nest, but the dominant individuals are going to lay the majority of the eggs. But in the process of this, about a third of all the eggs laid are destroyed. Fieldfares live in large colonies. These are birds that are fairly small and have difficult time defending their nest by themselves, but living in a colony, they can join forces and mob potential predators and reduce predation threats. However, a cost associated with living in a big colony is the fact that there is greater competition for food, and the nestlings that are not depredated oftentimes have a harder time surviving to the point of fledging. They suffer from greater starvation. So if you look at colony size, the nestling survival drops as colonies increase. And this is looking at nestlings that die because of starvation, not because of predation. These are the individuals that are not at least depredated. Cliff swallows live in large colonies, and the benefit of this is they forage on food sources that are unpredictable in time and space, and so they benefit from the colony serving as an information center. One of the costs, however, is a much higher parasite load as colonies increase in size. And these data here show that the number of parasite bugs per nestling, as that increases, the body mass of the nestling decreases. And one of the greatest predictors of survival in the first few weeks of life, once a bird fledges from the nest, is mass or their weight when they fledge. And so there's an obvious cost of being in large colonies, given that it reduces the mass of the nestlings. This is a photograph from a study that very dramatically indicated the physical costs of parasites in these swallow colonies. At half of the nests in the colony, they fumigated them to kill all of the parasites, and these two individuals shown in the picture here are of exactly the same age. The one on the left was from a nest that did not receive fumigant. The one on the right received fumigant, and you can see how much larger and healthier this individual is. Bluegills nest in colonies, and one of the costs associated with this is increased cuckoldry. So some males will lose out in paternity associated with their territory, their small little territory in these dense colonial aggregations. Benefits, though, some males are benefiting from the cuckoldry here, and all of the males are going to benefit to some degree in mutual nest defense or mobbing, preventing predators from being able to get and eat your eggs. You can see catfish here coming into this colony trying to eat some of the eggs. And again, not all of the individuals are going to be receiving the same benefit in this circumstance. Those on the edges are more likely to receive predation than those nesting in the center of the colony. So let's look at the different types of social interactions that you can see in a stable social group. Well, it shouldn't be surprising that selfish behaviors are pretty common in nature in social groups. If the best way to maximize your evolutionary goal is to be selfish, well, then that's what organisms will do. It's a kind of an everyone for themselves role in many cases. So we're going to be looking at this table in various ways, looking at how different behaviors affect a social donor and a social recipient. And selfish behavior would be indicated as the social donor, the selfish individual, gaining at the expense of a social recipient. Another potential interaction is spiteful behavior, in which the social donor does something to hurt a social recipient, but the consequence of that is they are also hurt. And the way we're measuring gain or loss is associated with direct reproductive success. So the social donor is trying to hinder the reproductive success or the direct reproductive success of a social recipient at a cost to themselves. Well, obviously, you should be thinking to yourself, that doesn't make any sense. And it doesn't. That is a behavior. Spiteful behaviors are not evolutionarily stable. Any gene that would contribute to a behavior such as this is reducing the potential for that gene to spread into future generations. So are there certain circumstances when individuals should help each other? Well, in some cases, yeah. Helping others may actually help you, and this is what we define as a mutualism. We've talked about mutualisms in the past, mobbing of predators, individuals receiving information about the distribution of resources at an information center. And so in this situation, the social donor gains and the social recipient gains. This is mutualism. In these circumstances, not all of the individuals are going to receive the same benefits to the same degree. For example, in male lions, they cooperate in some cases to take over a pride of females and then practice joint defense of these females. But males don't share the matings evenly in these prides. Alpha males can receive as much as 3.5 more copulations than the lowest ranking male in the pride. Why would the lowest ranking males even want to cooperate in this situation? Well, again, they may get at least some copulations, and they're making the best of a bad job. They would have no reproductive success on their own. Lazuli buntings have an interesting form of mutualism between some individuals. The brightest males are individuals that are the dominant individuals in a population. They settle first in territories after migration and defend these very large territories. And any male that's brightly colored or near their brightness, they try to keep those individuals from settling around them. These bright males will let dull brown males settle near them. These are individuals that are very low as far as dominant status goes. They're not greatly preferred by females, but if they occupy territory, they will recruit females. So they're not really a threat to extra-pair copulation to the bright males. But if they are going to be neighbors to the bright males, and they're going to be getting females into their territories, they will provide extra pair copulation opportunities for these brighter males. So again, what's the role of the brown males in this situation? They're not getting as much fitness, but at least they're getting some fitness. And the intermediates, individuals that are somewhat competitive to the dominant individuals, would be too much of a threat. And despite them having a higher dominance rank than the brownish individuals, the behavior of the dominant bright males excludes them from being able to occupy territories and reproduce. One final example, long-tailed manakins. Males will occupy lek display sites and work in pairs, these duos, to try to attract females. The alpha male and one subordinate male, a beta male, dance partner, do these very elaborate coordinated displays with synchronized calls and leaping. But only the alpha male mates. The males are unrelated, so it doesn't have anything to do with potential kin selection, which is a topic we'll be covering in a few slides. And there is no reciprocity, which is another topic we'll be talking about soon. But in short, it means they don't take turns mating. Only the alpha male mates. So in this situation, this is quite different from the previous examples where I was giving you the situation where the subordinate male was at least getting something. It doesn't appear that the subordinate male is getting anything in this case. Well, there is a strong dominance hierarchy in this species, and the alpha male obviously is getting all the copulations the beta male isn't. But after the alpha male dies, the beta male takes over the display area and becomes the new alpha male. So cooperation by the beta male ensures a good reputation and ensures a quality associated with the lek spot that they've been associated with. And females return year after year to the highest quality leks. So as you can see from the figure here, the previous alpha male, if he was successful and had a high number of copulations per hour, the new alpha male, that was formerly the beta male, will also have high reproductive success. So the beta male isn't getting anything initially, but eventually they will get benefits from these interactions. Well, are there circumstances in which individuals will help another individual with some short-term, small loss to themselves in the hopes of eventually getting some benefit out of it? Well, that describes a situation of reciprocity or reciprocal altruism. I'll help you now if you help me later. And as you can see from the figure here, the social donor first does something to advance the social recipient's cause. So initially they are hurt, but eventually they are receiving some benefit from this. Now, in a situation like this, what prevents cheaters from taking advantage of helpful suckers? So if it's you help me now and I'll help you later, what's to stop an individual from receiving that help and not returning the favor, not kind of following through with that promise for later help? Well, this has been modeled in what is referred to as the prisoner's dilemma. The prisoner's dilemma discusses a situation in which two individuals interact at a police station with the police, and these individuals can either agree to cooperate or they can be selfish. Here are their options. Well, the individuals work together to pull off some heist. They robbed a bank or something. The police pull them in for interrogation, and they know that the police have at least some evidence on them. But they also feel that if they can just cooperate, they're going to get minimum time in prison. And so there's a reward for mutual cooperation with a minimal prison sentence. However, the individuals are basically told by the police that if they cut a deal, they can really get off scot-free. But that means the individual that they're turning on is going to get a hefty punishment. So, and again, that's what happens if two suspects are brought in for questioning, they don't question them in the same room. They separate them to try to get them to work against each other. And so the police are telling both individuals in two different rooms at the same time, hey, we've got enough to put you guys away, but if you helped us build a stronger case and you told us everything you're going to get parole. But your partner, who we really think was the mastermind of this, is going to go to jail for a long time period. But they're telling both of these individuals this. So from the perspective of player A, who is going to be getting the reward in the situation, if player A defects, then they're going to get the deal, and their partners are going to go to prison for 10 years potentially. The table could be reversed so that if player B defects, but player A is the one that cooperates, player A is the sucker. And so this basically is not an evolutionarily stable situation as put forth here. So individuals have to be accountable for repayment of cooperation. There has to be some penalty for individuals to not cooperate. Otherwise, the only evolutionarily stable strategy, or ESS, is to be selfish. And that's what happens in the prisoner's dilemma, with both individuals defecting at once, the police basically backing out and say, well, there's no clear individual that we can credit with giving us the evidence, so we'll do kind of a sort of deal for both of you, but you're going to go away for a long time. And if they would have just cooperated, they could have had a better reward. But because of that temptation to defect, everything basically boils down to selfishness. So when can cooperation be an ESS? Well, that's only possible if the recipient of cooperative behavior meets up with cooperative individuals in the future. That cooperative individual, the individual that gave them some kind of benefit in the past, can then demand repayment. This sets up a conditions for the enforcement of reciprocity and what is called a tit-for-tat strategy. That tit-for-tat strategy becomes an evolutionarily stable strategy. So tit-for-tat is going to be a way that we can solve the prisoner's dilemma. Students oftentimes get these two terms confused. Prisoner's dilemma explains the problems associated with the evolution and stability of reciprocity. Tit-for-tat strategy is a situation that explains how it can be stable. So this is how tit-for-tat works. Individuals cooperate on their first encounter with another individual. And in the future, you just do whatever that individual did on the previous interaction. Let's say that you have a roommate that needs $5 at the end of the month. The beginning of the next month rolls around and you go up to your roommate and say, hey, you remember that $5 I gave you? I need it back. Okay. Well, if they give it back to you, well, then you just keep going. If they come to you in the future and ask for another $5, then you've got it, then you give it to them because you know they're good for it. However, if they do not return your $5, the next time they want to come begging for money from you, you're just going to say, no, last time I gave you $5, you didn't give it back to me, so I'm not giving you any more money. And that's one aspect of tit for tat. So tit for tat works because it's retaliatory, but it's also forgiving. Let's say that roommate that comes back and stiffed you for a day says, hey, man, sorry about that. I was being a real jerk. You're right. I owed you that money. Here it is. Then you're more likely to give them the money again in the future. So tit for tat can work when it's retaliatory for one step, but as soon as the individual does reciprocate, then it's forgiving and the pattern resets. So here's an example from vampire bats. Vampire bats leave a colony every night to search out a blood meal. And you can see that the weight of a bat, as it declines, puts them closer and closer to death from starvation. And when you're relatively fat, you're relatively happy. A single loss in weight is associated with moving you a little closer to starvation, but it's not moving you to starvation very quickly. However, when you're on the bottom end of this curve, losing a little bit of weight, you just don't have enough weight to lose, and it can drastically shift you much closer to starvation. So think about how that works with two bats that are returning to a colony at night. One bat is in fairly good shape and had a blood meal, was successful in finding food. Another roost mate comes in, didn't have luck the previous night, maybe the previous 2 nights. They're pretty low on their pre-fed weight, and they were unsuccessful that night again. Okay, they're really close to starvation. They're the individuals that are represented as the .R in this figure. Well, if they beg a blood meal from individual D, which is much healthier, much heavier weight, much farther away from starvation, that individual, if it regurgitates a blood meal from them, it's going to lose this much weight that puts them this much closer to starvation. But not a lot closer to starvation. It just moves them a little bit. But that same amount of weight gain that they're going to be transferring to the recipient, look at how much that shifts the recipient in this situation farther from death. It significantly is more beneficial to the recipient to receive the blood meal than it is costly for the donor to give the blood meal. And again, a week later, the tables may turn, and the individual that was the donor may now be the recipient in need, and guess who they're going to go beg their blood meal from? The previous individuals that they have donated blood to in the past. And this is possible because these bats live in stable social groups. They tend to roost in very predictable locations, and so you know where to find an individual when you need something from them. Another example of reciprocal altruism or reciprocity is mutual allopreening in primates. So individuals spend a little bit of time and energy preening other individuals, so there's some cost associated with that, but there's going to be a reciprocity associated with this. That's why it's called mutual allopreening. And overall, there's a net benefit to both individuals in this circumstance. Are there circumstances now when we can talk about individuals helping individuals and in the process hurting their own reproductive success? This defines altruism. And how can altruistic behaviors evolve by natural selection? So if the social donor provides a behavior that increases the direct reproductive success of a social recipient, how is that trait, assuming that it's got a genetic basis to it, going to be spread into the population if the social donor is hurting their own direct reproductive success? That's the challenge to understanding altruism. Well, really the key to understanding how altruism could evolve is understanding the relatedness of the individuals involved. Helping to improve the fitness of relatives can actually advance the evolutionary goal of an altruist. Okay, so let's revisit. What have I been saying throughout the semester that is the evolutionary goal of all organisms? I've been very careful to word that. The evolutionary goal is to pass on as many copies of your genes into future generations as possible. I haven't been saying to produce as many individual offspring as possible. That's one way of passing on your genes, but as we're going to see, that's not the only way. So really, individuals are trying to maximize inclusive fitness. So let's define what inclusive fitness is. Inclusive fitness is direct fitness plus indirect fitness. So let's break these two components of inclusive fitness apart and figure out how they can both contribute to inclusive fitness and which one of these is associated with altruism. Well, direct fitness is what we typically think about when we think about fitness. It's the gene copies that are produced by directly reproducing offspring. However, indirect fitness are gene copies produced by increasing the reproductive success or survival of closely related individuals. So in other words, altruistic behaviors can evolve if the gains in indirect fitness can compensate for losses in direct fitness. And why indirect fitness works and why this can be successful, it's because close relatives share many of the same genes. That's what it means to be related to an individual. You share a certain fraction of your genes with that individual. So traits that increase indirect fitness or maximize inclusive fitness via the indirect fitness component are said to evolve via kin selection. So let's try to understand how the degree of relatedness impacts the indirect fitness component. Well, parents pass on half of their genes to offspring in diploid species. But if you look at full siblings, they share on average the same proportion of genes. You get half of your genes from mom, half of your genes from dad, and at each locus, you have a 50% chance of sharing the same gene. So on average, you have 50% of the same genes with your full brothers and sisters. So helping mom and dad produce extra full siblings is actually just like you reproducing and producing offspring through the direct fitness component. Now, as you get to more distantly related individuals, the percentage of genes that you share is reduced, and the potential to gain indirect fitness is greatly reduced. Let's give a simple example of how inclusive fitness can be studied by looking at both the direct and indirect components of fitness. Let's say a population of birds can typically, in a pair, you see that there is the production of 2 fledglings on average. Well, that means if we look at the R, which is the fraction of genes that are shared, or the relatedness, R times 2 individuals. Well, the R in this situation, you're producing offspring, it's 0.5. So this is representing 1 fitness unit, 1 basic full copy of your genes. But let's say in this population, if this individual basically decided not to reproduce or was somehow prevented from reproducing, but instead went and helped mom and dad raise brothers and sisters, can they still achieve inclusive fitness through the indirect route? So in this example, this altruist is helping mom and dad produce siblings that are related to this individual by 0.5. Well, in this situation, they're producing 3 extra individuals. Remember, 2 of these individuals you can't count. Mom and dad could have done those on their own. So 3 individuals that you're helping them to produce extra above and beyond what they would have been able to do. 3 times 0.5 is 1.5 fitness units. So we have 0.5 fitness units improvement over direct fitness units that could be achieved through direct reproduction. So in this scenario, altruism is the best fitness tactic. For this altruistic individual, their best tactic is to not reproduce, but to help their mom and dad produce extra young. And again, just the logic associated with this, the altruistic individual can't count these 2 individuals because this is what mom and dad could have done on their own. These 2 individuals basically are making up for what the individual could have done on their own, because remember, full sibs and offspring are equally related. So this individual right here is the individual that tips the scales, making the altruism the best route. So they can actually gain more fitness through the indirect component than the direct component. People refer to Hamilton's rule to test when an altruistic gene should spread. Hamilton's rule is written as the benefits of altruism, how many extra young you help to produce, times your relatedness to those individuals. If that quantity is greater than the cost, times the relatedness of the individuals that are lost through not direct reproduction, which in this case is going to be always 0.5, as long as that ratio is tipping to the benefit of the left of the equation, then altruism should evolve. If an individual has the choice of producing 1 offspring or 3 additional nephews, what should they do? Well, let's put in the numbers. Nephews, you're related to your nephew by 0.25, so 3 times 0.25 is greater than 1 times 0.5. That's how you would be related to your offspring. Altruism would be the most beneficial way that you could derive inclusive fitness under these circumstances. Another formulation of Hamilton's rule is relatedness times the number of beneficiaries that you're helping to produce, the extra number of individuals, minus the cost of that you're losing either through direct reproduction or your own survival, as long as that quantity is greater than zero. And sometimes this formula is a little bit better to look at when you consider another way altruistic behaviors have been studied to potentially be beneficial. They can also evolve when you save the life of a certain number of close relatives. So, for example, an altruistic individual will sacrifice itself if that action can save the lives of 2 full sibs. You are related to yourself by 1. 2 full sibs on average are related to you to the same degree, or full half sibs, or full nieces or nephews, which are at 0.25. But again, it gets a little less realistic as you go down to lesser related individuals. If you could save the life of 8 cousins by sacrificing your life, again, that would still be a break-even point. So 9 cousins is what it would have to take for you to be able to save their life by somehow sacrificing your life. That would be in your own fitness interests. So let's look at an example of this. In some cases, it's kind of difficult to determine whether a behavior is mutualistic or altruistic. So let's look at Belding's ground squirrels. They produce alarm calls when they see predators. And if the predator is an aerial predator, this actually represents mutualism. It's warning group members to go duck and find cover, but it's also telling the predator, hey, I see you, so if you're going to attack anybody, don't attack me. However, alarm calls for terrestrial predators do represent altruism. The alarm callers are more likely to suffer the predatory attack and suffer higher predation rates. And alarm calls are mainly females in this species. And this is because the females are more likely to have relatives in the group, and they reduce their call rates when they're in groups without relatives. And that can be shown from the data here. Males greater than 1 year old that have dispersed from their natal colony and they've just entered a colony and they haven't bred yet, they don't have any relatives nearby. And so if you look at the expected number of calls that are produced that should have come from their class, 28% of the calls in this population should have come from them, but they only contributed calls 18% of the time. So they're showing selfish behavior in that regard. Females greater than 1 year old, though, that do have living relatives in the coterie or that group of squirrels, again, are only expected to produce 28% of the calls, but they're producing 39%, a much higher percentage of calls than they would be expected to do. So they're clearly demonstrating altruistic calls in this situation, because this is associated with exposure to terrestrial predators. But it's not just that it's females. Females that don't have the same egg class, that just don't have any living relatives because they may not have had reproductive success in the previous year or something, they fit the pattern of the males. They do not produce the calls as you would expect. So this is indicating that this altruistic act, if it has the potential to benefit close relatives, is more likely to be seen. So in review, social living has potential costs and benefits that vary among species. The social interactions we discussed, selfish behaviors, obviously pretty common in nature. Individuals are basically doing something to maximize their own fitness. If it happens to hurt other individuals, well, that's just the way it is. Spiteful behaviors are not really evolutionarily stable. There are no really good examples of a behavior that hurts a competitor's fitness but also hurts the actor that's providing that behavior, because how would that gene for that behavior be passed on to future generations? Mutualisms are not uncommon in social species. The benefits to each individual basically reinforce these behaviors, but again, the benefits may not always be shared equally among individuals, especially if there's a strong dominant-subordinate hierarchy in the social group. We also talked about reciprocal altruism or reciprocity. This is extended exchange of mutualistic actions between individuals. So individuals overall are gaining in a mutualistic way, but at any interaction, the actor is losing something. They're actually being hurt temporarily by something for the other individual's gain. But if this is a stable situation. In the long run, it's mutualistic for all individuals. Now, there is the potential for invasion of cheater individuals in this situation, and that's described by the prisoner's dilemma. But what can defeat the prisoner's dilemma and add stability to the process depends on a way to enforce reciprocity for altruistic acts. And we talked about tit for tat as being a strategy that led to that stability. And lastly, we talked about altruism, how individuals can lose direct fitness due to altruistic acts, and how can that be evolutionarily stable. And to understand altruism, you have to understand inclusive fitness, which is both direct fitness and indirect fitness. Altruism is adaptive if indirect fitness gains can compensate for losses in direct fitness. How do you get indirect fitness gains? Well, they're one of two ways. You can increase the production of extra young by close relatives. You can't count the young that they could have produced on their own. Or you can save the lives of a number of close relatives that would have died without your actions. And as long as the conditions of Hamilton's rule are met, then kin selection will lead to the evolution of these altruistic behaviors.